Welcome back. Let us resume our discussion on the comparator design that we are looking at. Remember, starting from the ADC specifications, we arrived at some of the important specification of the comparator. Before that, we discussed some other constituent of the ADC, the single slope ADC, namely the sampling unit, where we discussed the transistor level details of the sampling units, what are the non-agilities that are going to come when we look at transistor level implementation of a simple transmission gate based sampling switch. And after that, we looked into the ramp circuit. What are the issues associated with building a ramp circuit? We looked into the required value of the capacitors and the charging current magnitude, and also the implementation of the current source, which is supposed to be used. We should have sufficiently wide range as well as a relatively flat slope with respect to the output voltage, or in other words, a high output impedance, but low output, low voltage headroom. And next, we also derived the specification of the ADC starting from specification of the comparator starting from the high level specification of the ADC. We looked at the required clock frequency for the counter, and from there we arrived at the required gain and the bandwidth of the ADC. And the required gain value was around say 400, and the gain bandwidth product that we are looking at was around 1 megahertz. We have the bandwidth of the amplifier around 250 kilohertz. So, these are the values we estimated, and based on these we need to look into the design of the comparator and specify the first of all the sizing depending upon the gain and bandwidth values. Also, one of the targets would be to minimize the bias current, because ultimately it is a area constraint and power constraint design, where we are supposed to minimize area of the single channel acquiring the biopotential, and along with that we are also supposed to minimize the overall bias current in different analog units. So, we have seen that the power budget allocated to the front end design, front end amplifiers, that was close to say 10 to 20 microampere. Likewise, in the filters we had relatively lower bias current because of use of subthreshold circuits for implementing the GMC filters, and therefore, that block was a relatively lower power consumption block. And likewise, in the ADC we need to look at the different power components and make sure that the overall power dissipation is relatively low or relatively limited as compared to the front end. It should not go beyond the front end, otherwise the ADC will become the dominant power consuming block. And remember, the decision regarding the choice of the ADC topology also depends upon the performance of the ADC that we are able to get. It should be able to meet the sampling speed requirement, it should be able to meet the resolution requirement. At the same time, it should also be able to satisfy the power constraint. We should be able to get the required resolution and sampling speed with the given power constraint. So, looking at the selected topology, of course, we have to make sure that the constituent building blocks, namely the comparator, the sampling unit, the ramping circuit, and the digital units taken together, it do not consume a lot of power. We would like to limit the total power budget maybe lower than 20 microwatt, or maybe significantly lower than that, so that its power budget is a relatively smaller fraction of the entire power budget allocated to the signal processing chain. So, towards that end, we can set up a convenient upper limit on the bias current that we are going to apply for the comparator. If you look at the different blocks that we have discussed so far, in the analog domain, the sampling switch, the ramping circuit, and the comparator, the block which is consuming static power is basically the comparator, and therefore, we expect that in the analog domain the comparator is going to be the most power hungry unit in the entire ADC, and therefore, it would be important to minimize the power dissipation in the comparator. And therefore, if I set a constraint upper limit of bias current say 10 microampere for the comparator, we can start with that constraint and see whether the most important criteria of the gain and bandwidth is being met. Along with that, we also have the constraint of input swing. If you remember, the input swing or input common mode range, that would be dictated by the maximum peak to peak swing provided by the last stage amplification, and we have seen that it is convenient to get almost nearly full swing signals from the last stage amplification. If you have a common source stage after the diff amp forming the last stage of the op amp, then we can expect almost full swing coming out of that stage, and hence the input swing, I can say input swing or input range that the comparator should have is going to be almost equal to VDD, 0 to VDD, in our case 2 volt. And it would not be wrong to equate this required input swing to common mode range of the amplifier that we are building, the comparator that we are building. So, I can write this at input common mode range. We will see why it is equivalent to input common mode range. So, if you look at the overall operation of the comparator that is going to be connected to our ramping circuitry and the input signal, suppose we are having the 2-stage amplifier as our comparator. Remember, the purpose is to detect the cross point when the V ramp or the ramping signal on the capacitor is crossing the reference signal V ref. This is the point at which the comparator is supposed to make the transition. So, if the polarity is such that you are having the input signal or the input signals coming at the positive terminal, you have the sampled input signal coming at the positive terminal, and you have the V ramp or the capacitor voltage ramping up on the negative terminal, then the transition between high to low should happen close to this point. If you are far away from these 2 points and the comparator gain is large enough, definitely the comparator output will be deterministic. If the V ref is sufficiently different from this sampled value of V in, definitely the output will be close to VDD or ground. But the moment V ref approaches the sampled voltage, that is the region or the crucial instance at which we should be getting timely resolution, timely switching of the comparator. So, if the response of the comparator is fast enough and the gain is sufficiently large, whenever there is a whenever the ramping signal crosses the reference or the stored sampled signal by a small amount delta V, it will be able to switch, provided delta V times A is equal to the full swing as we have designed earlier. So, we are interested in the comparator transient close to this particular point, and therefore, at that point we can see that both these signals are going to be almost close together, right. And at that particular point, I have to make sure that the comparator is going to work fine for the sampled input level, because if the input level sampled is too low, I would expect that the comparator should work fine while the V ref is very small, the ramping voltage is very small, equal to the sampled input voltage. Likewise, on the other hand, if the sampled voltage is constant and it is pretty large, we would also expect that the comparator should also work fine. It should the transition of the comparator should be fast enough even when your ramp is approaching the sample voltage, which is high. So, irrespective of the sample input voltage, at all these points the comparator should be well behaved, and for that it would require that the input common mode range of the comparator is large enough, starting from 0 all the way to VDD, because as we see, the critical point is when these 2 signals are close together. The sampled signal Vs, Vs and Vs and the ramping Vref is whenever they are getting close together, that means the comparator is both the inputs of the comparator are close together, and we are supposed to detect a small difference or change in polarity of V in 1 minus V in 2 at that particular point. And for that we must make sure that even for low input voltages as well as very high input voltages approaching VDD, it should be working, and that is the definition of input common mode range, right. So, if you want to make sure that the gain of the comparator is sufficiently high, all the transistors in the amplifier are maintained in saturation for the entire range of the input common mode level, that is termed as the input that maximum range for which all the transistors, maximum range of the common mode input for which all the transistors remain in saturation, that is termed as the input common mode range. So, essentially for a reliable operation, what we are looking at is that the input common mode range of the amplifier should be rail to rail. That means it should be able to handle rail to rail input swing. That means when both the inputs are close together and you are having basically effectively common mode applied as the input, common mode input applied at the gates, the amplifier should be able to operate with high gain for the entire rail to rail swing of the common mode, or in other words it should be able to maintain high gain for the entire range of the input common mode. So, that is one of the prime requirements, and as we will see as per our previous discussion, one of the main challenges will be maintaining the input common mode range. You of course have the requirement for the gain and bandwidth, which once again may not be so critical in this case, because ultimately we are talking about an open loop amplifier where we can have relatively higher bandwidth, and the open loop gain can also be sufficiently large. So, these two may not be very critical, whereas having a large input common mode range, that will become a major bottleneck for the comparator that we are looking at. So, for looking at the gain and bandwidth, once again we can just identify that what are the quantities, what are the transistor parameters which are going to affect my gain and bandwidth, and that is going to give me the direction for sizing, what approach should I take, which transistor should I size in what manner, what should be the channel length, what should be the bias current, and so on, in order to size the transistor in appropriate direction. If you are not meeting the specs, you can go back and change the sizing. So, if you look at the application that we are concerned with, here we are expecting that the output of this comparator is going to be given to some digital circuitry, because there is supposed to be a digital level. If it is not having full swing, then probably we can keep an inverter, digital inverter, which can convert this comparator output into full swing. We will be looking into the details of digital comparator, digital inverter, and its interfacing with analog circuitry, what are the associated concerns, but ultimately we want a full swing digital output out of the comparator. That is the functionality of an ideal comparator. So, we would like to have this full swing. So, in general, for the digital comparator, or sorry, a digital inverter, the parasitic capacitance at the input node may be once again of the order of few femtofarads to at the max few tens of femtofarad, and therefore, the overall parasitic capacitance over here may be still dominated by the transistors of the amplifier itself. Therefore, what we can say is in the overall case, if you are not having any significant load capacitance over here, in that case the pole over here can become the dominant one. Of course, it depends upon the condition. Means if your comparator output is feeding a lot of other logic gates, and you are having a lot of other digital circuitry being driven by this output, then it can become a dominant node. You can have a large capacitance over here. But if I assume that the load is simple, it is just a simple inverter which is minimum size, then this point may be giving you the dominant pole, because you are having at least a Miller multiplication for the CGD for this particular MOSFET, and as a result for similar dimensions of the MOSFETs and similar value of ID, similar value of RO, we expect that the Miller multiplication of CGD will provide larger capacitance, larger effective capacitance at this node, and hence this can be the dominant pole, limiting the overall bandwidth. So, effectively what I can write is that the overall gain of my comparator, which is going to depend upon say GM1 RO1 and GM2 RO2, and the bandwidth, if I say, is going to depend upon the first node over here. I can write this as 1 upon R equivalent C equivalent at that node, and therefore, we have the RO1 of the first stage and C equivalent. If I assume once again that CGD is the dominant component, Miller multiplied CGD is the dominant component, then I will have the gain of the second stage GM2 RO2 times the CGD coming into picture. CGD of I can write it down as CGD of 6 coming into picture. So, again I can preserve the Roman letters for depicting the stages and the specific numbers, the Roman the decimal numbers to depict the transistor number. So, CGD 6 basically appears as the effective load capacitance, and because of Miller multiplication you are going to have a dominant pole over here. Now, if I look at the gain bandwidth product once again I have the GM2 RO2 getting cancelled, and you have RO1 getting cancelled, and you are having effectively GM1 upon CGD6 determining the gain bandwidth product. And therefore, we would need a, if you want a sufficiently large gain bandwidth product, you should make the GM1 sufficiently large. And what would CGD6 depend upon? Approximately, if I say it is going to depend upon the C overlap, where C overlap is the overlap capacitance per unit width of the MOSFET times the W of M6. Remember, how does the C overlap comes into picture? In the saturation region, you have the C overlap coming because of the CGD coming because of the C overlap, because of the gate overlapping with the drain and drain region, and then the magnitude of this effective capacitance is proportional to the the magnitude of the effective capacitance which arises because of this overlap is going to be proportional to the W. So, larger is the W, larger is the effective area of this overlap. So, it is not so much dependent upon L, it is dependent upon the L overlap, which is technology parameter, and the W. So, we can say that this is going to be the dependency of the gain bandwidth product, and we have also the dependency of the gain and the bandwidth individually. So, this can be the equations which are going to govern our design steps. Based on this, we can iterate with a given starting point and try to see in which direction to move. So, I can start with a bias current budget, say IB equal to 10 microampere, and for that I have the overall gain to be determined. If I assume once again that I am bifurcating the gain equally into two stages, therefore, a gain of 20 from each stage. So, GM1 RO1 I am targeting to be 20, likewise GM2 RO2 also I am trying to be set to 20. That would imply GM1 RO1 is equal to around 20, and from here I have the dependencies of both these terms. I can look at the dependencies. You have the bias current ID1 in the first stage and W by L of the first stage, and likewise RO you have 1 upon lambda ID 1, and again lambda is dependent upon lambda dash times upon L. So, this is a quantity which is inversely proportional to L. So, I will get L1 in the denominator. So, if I assume that the RO of this device is dominant, so in that case I will get the W1 L1, and you have the ID 1 coming in the denominator, and you have the lambda dash. So, basically the design parameters that we see, the dependencies are W1 L1 upon ID 1 for the M1. And if I assume that we are choosing L1 which is common to all transistors just to get a sufficient RO, we can keep the same length, almost similar length for all the transistors. Remember, here we are not worried about noise constraints, so we do not have sizing constraint on L so severely. So, let us assume that we are going to determine a certain L for which we can find out the required W1, so that we get a certain gain. So, let us say that for the ID budget that we have chosen 10 micro, we can divide it into two halves. So, I can assume 5 microampere bias current over here, another 5 microampere bias current over here. That gives me the ID 1 of the first stage. So, this is something we have started with, and likewise I have the L1 which I can start with. I can start with a nominal value of L1, you can keep it say 0.5 micrometer, and you have a ID 1 in both the stages. For that, basically I need to determine what is the W1, so that you get a sufficient gain of 20 from the first stage. So, for this L1 I can determine the value of minimum value of W1, so that a gain of around 20 is achieved in the first stage. And likewise, if I use the same channel length in the output stage and almost similar bias current in the output stage, I have the corresponding value of RO2 coming into picture, and therefore, the GM requirement is also similar, and therefore, the W by L and RO are going to be related over here. So, when I have this W1 and L1 in the first stage determined, that for this particular channel length I need a certain W1 to get a 20 gain. It also gives me the W1 for the W for the second stage transistors, and also we have assumed that the channel lengths are similar. So, I get the W1 for the second stage transistors also to get the similar GM2 RO2 value. Now, the next thing is once for this A1 which is root under W1 L1 upon ID 1, this is a proportionality. So, once for this I have determined the W1 required for a selected 0.5 micro, determine get the W1 needed for A of 20, A1 of 20. This also gives the W2 for the input stage of the it also gives the W of the M6, because the GMs are taken to be almost similar. So, it also gives me the W2 of M6, and also I have the L of the M6 taken as same value. So, I have the W2 determined, and corresponding to that I have the bandwidth determined by the equation over here. So, if I have the overall bandwidth given by RO1, GM1, RO2, CGD6. So, I know that if I am keeping the same W1, the bandwidth is mainly going to be determined by the quantity over here. So, for the predetermined value of RO1, GM1, RO2 and the CGD6, which is ultimately coming from the W by L or W of M6, I can check whether the bandwidth condition is met. If it is not met, then once again we have to go back and tweak my choices over here, so that I can move in the right direction. So, I have set the gain and checking for the bandwidth. So, if the bandwidth condition is such that the obtained bandwidth is much lower than what I expected, then I need to go back and tweak the parameters over here, such that the gain is remaining more or less intact, but the bandwidth is enhanced. So, in order to do that, once again we can have several options over here. So, suppose case 1 you have the bandwidth lower than required. So, in that case I would like to keep the gain as it is, while I would like to increase the overall bandwidth. So, if I say that this is the quantity on which my gain dependent, and I have to increase the overall bandwidth while keeping the gain constant. So, I would like to keep this ratio almost similar, while I can try to go back and look at the bandwidth equation and try to increase this quantity. And here once again, if I look at the bandwidth, I have the bandwidth given by RO1, GM2, RO2 and CGD6, and as we have seen this quantity, once again I have the RO1 given by I am just writing the design parameters on which I am dependent. So, I have the RO1 given by 1 upon lambda ID1. So, I have lambda 1 ID1, which is again our chosen quantity, and this is once again proportional to L. So, this is L1, which is also our chosen quantity already, and then I have the GM2, which is once again going to depend upon root under W by L2, and you have the RO2, which is once again dependent upon ID, which is similar in both the cases. So, ID1 times L 1, which is also similar in both the cases, and then again C overlap times you have the CGD6, which is dependent upon W6. So, once again this is the bandwidth I have to increase the bandwidth while keeping the gain constant. So, I should make sure that this product WL upon ID is remaining all more or less constant, while I am able to tweak this quantity over here, the parameters over here, so that the bandwidth gets improved. So, if I look at the if I look at the overall quantities over here, so I have the bandwidth dependence on ID definitely pretty strong. So, you have the ID so I have just so this I just messed up. Let me write it down once again. So, you have RO1, which is ID1 times lambda ID. So, basically it is lambda dash upon L1, and likewise you have RO2, which is ID2 lambda 2 upon L2, and you have the GM2, which is going to be proportional to ID2 W by L2, and you have the CGD6, which is proportional to W2 times the C overlap, which is a technology parameter. This is not in our hand. Likewise, these two are also not in our hand. So, I can get rid of these, and I am left with this particular quantity. And once again, if I assume that the overall bias current is similar in both the cases. So, these are just going to give me the same values of bias current, and therefore, I have a strong dependence on ID. So, I have ID to the power of 3 by 2 coming over here, and then I also have L square coming over here, or rather L to the power of 3 by 2 coming over here, and likewise I have we can say W 2 times root under W2, so W to the power of 3 by 2 coming over here. So these are the quantities I am seeing. So ID upon L times W to the power of 3 by 2, and as a result I can this is W2. So I can the target would be finally to increase this quantity while keeping the other one same, and to do that, one option is that okay, you can increase the ID one. So we can look at one particular option. Let us increase ID, and that would increase the power consumption overall, and here correspondingly we have to increase the W and L product, so that the overall gain is reduced. So power consumption, if we want to keep it under control, we would like to avoid this option. Second option may be that okay, you can increase the L and W2. Now if I increase the if I reduce if I reduce the W2, that is another option. So for a given L, if I am reducing the W2 while I am increasing the ID by the same factor, that can be one option. So I can increase I can reduce the W2 so that the bandwidth goes up, and now I have in the second in the first stage, of course the gain will remain almost similar if I am not tweaking these parameters, but if I am reducing the W2, I will end up reducing the gain of the second stage, which is the GM2 of the second stage, and that can be compensated, for example, by say increasing the W1 of the first stage. So I can go up and increase the W1 by the same factor, so that the A1 is going up by the same factor, whereas A2 is going down a little bit, so that the A1 A2 product is being maintained while reducing the overall or increasing the overall bandwidth. So we can see the directions to be taken up. So since the overall gain can be bifurcated in an uneven fashion, I can try to divert more gain toward the first stage and lesser toward the second stage, and try to push the pole towards higher frequency by choosing a W2 which is smaller, because a smaller W2 would imply a smaller CGD and hence higher bandwidth, lower Miller multiplication and higher bandwidth. So this is another concern that we can have. Now if we are able to do that, another target would be that we would like to reduce the bias current also as much as possible, so that the gain and bandwidth both are maintained while achieving limited power consumption in the amplifier. So for that we can see once again these two operations. If you have to lower the power, suppose we have achieved this appropriate bifurcation between A1 and A2, so that the overall gain and bandwidth is now being met. Now if that is being met, now another target is to check whether we can reduce ID further. So again these two equations are going to give me some direction regarding that. So we can see if I reduce the ID over here, the gain in the first stage may go up once again, but however the bandwidth over here will be getting limited. And however, once again if I want to keep the bandwidth also sufficiently high, that would mean that I need to once again reduce the L. So rather than choosing the same L, I can go for an L2 which is smaller. So in order to reduce I bias, once again I look at the two equations, the gain of the first stage which is W1 L1 upon ID1, and I can look at the the overall bandwidth dependency ID upon L2 W2 to the power of 3 by 2, and suppose by the previous step we have obtained a proper bifurcation of gain, A1 is sufficient, A2 is also sufficient, we would and we are meeting the bandwidth. Now our target is to say our target is to save some bias current by pushing the ID down. So if I push the ID down here, once again we are getting reduction in A1, sorry, increase in A1, so A1 will go up. At the same time, in order to keep the bandwidth same, I will have to either lower L2 or W2. So if I do that, say I reduce the L2 by the same magnitude. So, that would once again imply that the overall gain for the second stage, which is also proportional to root under W2 L2 upon ID2, that will be going down, and in order to avoid that, once again I have to make sure that the gain reduction in the second stage is corresponding to the gain increase in the first stage. So, if the magnitudes are similar, then I do not worry so much. So, once again I have an option that despite reducing the L2 and reducing the ID simultaneously to keep the same bandwidth, I can achieve overall similar gain, because the gain of the first stage has been made slightly higher. So, there are the directions we can take up step by step, and if you are aware of the dependencies, that from where the dominant capacitance is coming, from where the RO, the significant RO part is coming, which device dimension affects the parasitics in what manner. So, then we have the right directions we can tweak with we can make informed decision about the sizing. So, of course, in the simulations, whenever we tweak the device dimensions, we can get the appropriate path based on the intuition, based on the information about the dependencies that we have, we can get the appropriate path. But if we have clear information about the dependencies, even without these derivations, at least if we have the higher level information in mind, that okay, means how the critical pole is getting originated, how the bias current, how the sizing of the input device is going to improve or degrade the gain, on what critical parameters, which device dimension the bandwidth is going to dominate, depend. Based on that, we can do the sizing in the right direction. So, here we show that we started with a certain given bias current and a certain channel length, and assuming equal gain division, we looked into the WL required for obtaining a certain gain, because we have the WL of the input device determining the overall gain for a given ID and L. And then we went to the bandwidth component and verified whether the bandwidth is being met. If not, then once again we have to tweak these two quantities in a certain way, so that the bandwidth is increased without degrading the gain. And the second thing is we also need to reduce the power consumption. So, for that, once again we can try to reduce the bias current while making sure that the gain is maintained and the bandwidth is maintained while meeting the power specs. So, this is the way we can approach a design problem. Just having the right direction regarding the dependencies is going to help us in achieving the right specs for the gain, bandwidth, as well as minimizing the overall bias current. So, there is no unique algorithm, there is no unique set of steps. Depending upon the specification, depending upon the requirement, the load conditions, etc., you may have to look at your sizing consideration. If the condition would have been different and you would have been you had a large load capacitance over here, so that the bandwidth dependency is really over here, then the sizing constraint would be different. So, here I have just tried to derive the sizing consideration for this particular condition. So, this is regarding the sizing with respect to the gain, and now gain and bandwidth while reducing the power consumption. Now, the other constraint that we mentioned in the very beginning is ICMR, where the input common mode range must be full swing, close to full swing. There, if you look at the criteria, the input device size is going to determine the ICMR on the lower side. Remember, what is the minimum input common mode voltage that you can apply at the input? If I look at the ICMR requirement, which I said is going to be more critical than the other constraint of gain, bandwidth, and power. So, if I look at the ICMR, the VCM min depends upon the VG5 minus VT. For a given VG5 bias point over here, VG5 minus VT is the minimum voltage, and plus VGS of 1 is the gate voltage of the input device. So, this is the minimum gate voltage that you can have while keeping the M5 in saturation. If you go below that, then the drain voltage of M5 will be falling below Vg minus Vt, and as a result this transistor will be entering into triode region. And hence, if I look at this overall quantity, we have this term which is basically represented as a V overdrive of the M5, and I can of course try to size the M5 as much as possible, so that the overdrive voltage goes down. Remember, the overdrive voltage depends upon the size inversely. So, I can size the M5 larger for a given bias current, so that the V overdrive goes down. VGS1 can also be written as VT1 plus V overdrive 1, because V overdrive is once again VGS minus VT. So, this is V overdrive 1. Once again I can depending upon this bias current, I can afford to increase the W by L, or I can check whether for the given W by L that is coming from our previous step, the V overdrive 1 is sufficiently small. If you try to change or reduce the V overdrive over here, then of course you remember that the gain and the bandwidth are again going to get affected. So, if you try to improve the overdrive voltage of M1, then of course you have to back annotate and check whether your gain bandwidth requirements are not getting violated. So, suppose we are having sufficiently low overdrive 1 and overdrive 2, because bias current is sufficiently small. So, a nominal size of W by L for even W by L of around 10 or 20 may give you overdrive voltage which are sufficiently small, maybe few tens of millivolts. So, in that case I can ignore these two, but this is the component which is remaining, which is going to be say 0.4 volt for a nominal MOSFET, and therefore, on the lower side they are the VT of these transistors ultimately going to limit my VCM min. On the other hand, VCM max, I want to say VCM max, if your common mode voltage is increasing, remember the drain potentials over here remain almost clamped to the VDD minus VGP. So, this is VDD minus VDD minus VSGP. So, this is if I assume that this is the source to gate potential drop VSG of this PMOS. So, this potential is VDD minus VSGP, and remember for this differential amplifier with current mirror load, if you are increasing this input gate potential, if I assume that both of them are close together, the output potential over here will be close to the diode connected voltage over here, but this will be following they will be close to the required value VSG VDD minus VSG. And as a result, the maximum potential you can have at the gate of M1 and M2 while keeping these two in saturation is going to be VDD minus VSGP plus mod VT plus VTN or VT1 or VT2, because remember, if this potential is clamped to VDD minus VSG and you are trying to increase these two gate voltages, ultimately these two transistors will enter into triode when the gate potential crosses the drain plus VT. So, once again we have I can represent this VSG as the V overdrive of P plus mod VTP, and I have VT1. So, if I assume that VTN or VT1 and VTP are almost similar, then I am left with just VDD minus V overdrive P, and therefore, if I choose the W by L of these two transistors sufficiently large over here, I can reduce the V overdrive significantly. So, remember that in the bandwidth and gain also these do not play a very significant role as of the given condition, and therefore, I can afford to increase the W by L of these transistors, so that the V overdrive is almost negligible as compared to VT, and I can safely increase the upper VCM max. Therefore, the limitation is coming from the lower side, in this case VCM min for the differential amplifier with NMOS input. So, let us see couple of ways in which we can mitigate this, and we can achieve full swing or rail to rail input common mode range, so that our ADC can work for the entire range of the output provided by the analog amplification chain. Let us take a break before we can resume our discussion.